Welcome to Jump On again, another session of Jump On Tuesday. Today we'll be talking about yield improvement with predictive modeling and design of experiment. All right, so we should have a good number of attendees. So I'm gonna start soon. So welcome everyone. So today we're gonna be listening to our guest speaker, invited speaker, Dr. Pradeep Sharma. He is the principal engineer from the manufacturing quality with NXP Taiwan. So he has 10 plus years experience in quality and reliability related roles in the high tech and manufacturing sector. So currently he's driving the automotive excellence with Six Sigma quality tools and big data analytics, AI and ML in NXP. So these are some other details about Dr. Pradeep Sharma. So if you guys want to connect with him, you guys can connect with him through LinkedIn, scan his QR code available here, or I will share his profile in the chat later. Okay. A bit of promotion. So we're going to have a decision tree based method and predictive modeling session on the 22nd of July. However, this is with our Australia and New Zealand team. So it will be on the 22nd of July at 10 a.m. Australia time. It's a lunch and learn session. I will share the link to the event later during the chat. All right, if you guys are ready, Dr. Pradeep, are you ready? Okay, yes, I can see your screen.
Okay, so we still have the polls going on. Okay, so welcome everyone. And first of all, big welcome. It's your webinar, okay? And I really wish to get many questions from you, either in this session or connect me on LinkedIn or wherever you like, okay? And at least I'll be sharing the PDF file of this presentation because I have got all the permissions required to really share it, okay? And let's start it, okay? So I have quite a significant experience in the PCB manufacturing for the reliability testing, for the RF testing, and I've been working as IEEE senior member. Recently started to engage with data analytics, and I see things are changing, and there is some opportunity that I might want to share with you that what GEM can offer us and how we can leverage the power of the analytics to solve some of the simpler problems. And for a complex one, of course, we need better tools. Okay, right. Hey, let's go to. So what we're going to look into today's call is that how we use the data modeling to identify what's important by analyzing old data. So we try to do some predictive stuff. Okay. And then we understand what is important, what's not important, connect with our suppliers, connect with our subject matter experts, and then, okay, this is what seems to be value to us to be really able to have a good yield. And by the way, the concept of yield here is not the manufacturing yield. Okay, for us, this is more like time to failure of a certain PCB. When a device is mounted in that, we do temperature cycling or some other reliability tests. The PCB should not fail. That's one of the important things that we have to ensure to avoid any repeat or requalification or having unnecessary ADs and the failure analysis and all those kind of things. Okay. Now, once we understand what's important, what are the key variables, then we run the Taguchi analysis, because I can assure you, when you are running a PCB, you have at least more than 20 variables from design, from manufacturing, from quality. And if you're not really the kind of expert, then it's best to run a Taguchi optimization. You may try to play with some noise factors in the background if that is required. Okay. But somehow we were able to deploy the ordinary Taguchi DOE metrics. We did the experiments. We were able to extend our time to failure. And that was good news for us. Okay. So today I want to share you what exactly we did and what are the different things happening in the background. Okay. But before we jump into that, I take liberty of some sort of liberty that, okay, yeah, maybe all the audience do not have the idea what a printed circuit board, what's the process behind. We all have seen the PCB in our cell phones. We have seen the PCBs in our computers, if you have ever opened one. Okay. So this is the general process. We could get an ODB design, Gerber file design. Okay. And one simple note for everyone, as a just tip of the day, please make sure you share an ODB plus design to your suppliers. If you don't want to miss any via or anything, any special art thing you don't want to miss, make sure you share ODB plus file instead of traditional Gerber file, which are exchanged over the emails, which are easy to be shared. But sometimes I have seen that things may drop. Okay. So once we got a design, we got design rule checks, design for manufacturing check. Then we start to prepare the inner layer, outer layer, do certain optical inspections, laminations, drilling, plating, etching, surface finish. If some people need cell screen or solder mask, that's also deployed. Then there's outer layer etching, profiling, some electrical testing. We did do some open shore or impedance testing to really make sure the product really meets the requirement. Sometimes we may even have RF impedance matching requirements, visual inspections, and then the delivery. So this is the general concept of the manufacturing. Now, what we normally see as defects, delamination between the layers, or maybe the solder mask not adhering very well, or there's a trace which is broken, or there are lots of vias which are which have cracked after testing, or it could be just immediately after manufacturing. So there could be manufacturing yield loss, there could be yield loss after reliability, but for today's call, we're more concerned about the yield loss after reliability testing. Okay. We could also see like conductive or corrosive particles. There could be copper particles or other metal particles trapped between the different layers of the sub PCB that could cause the latent fails. For RF signals, there could be signal integrity issue because of the BOM, because of the design, because of the manufacturing impact on the particular BOM. BOM refers to the bill of material. That's the material that we select for the manufacturing. Okay. And then there could be hundreds of cosmetic defects which are looked into, and we have IPC guidelines, and we can really screen them out without facing a risk of customer returns or reliability qualification fails. Okay. Now, what would be the exact Pareto of those things? I think the answer to that really depends. Who is your supplier? What's the grade of that supplier? Is that the top 20 suppliers around the world who supply for the biggest automotive customers? Or is it just a small scale industry player in the local area? What kind of material we have used? And all those things would generate a different Pareto for different suppliers. Okay, so that's the reason why we didn't want to point out anything specific as a kind of Pareto. But yes, this would generally cover most of the things that we face after different kind of testing, be temperature cycling testing, board level reliability testing. Okay. Now, coming to the problem description that we have for today's call. So when we started our normalized yield, okay, it's not 80% or something, probably we were having 90, 95% or even higher, but then we started to see some fluctuations happen. So what was happening as a function of time, if I look at the normalized yield, probably in the beginning, maybe a couple of years ago, we have simpler products. Then we started to launch into IoT. We got a lot of car radar applications, a lot of engine controller applications, and the things are becoming more complicated. And then we started to see a flavor that, okay, with these complex products coming in, the reliability yield of these products is suffering a bit. There's significant fluctuations. And these can possibly be understood in terms of the interaction of the PCB with the device we mount on. For example, if this is a QFN, QFP, then you might see, okay, the leads where they connect to the trace or the vias below this device, okay, those could become sensitive zones where the device would be interacting with the PCB. And for BGA, that's even more interesting. We have BGA bolts. There's another additional layer, which is very sensitive to the temperature cycling crack or HTOL, okay? And also sensitive if you're doing the board level reliability test, like if you just drop 50 times, 100 times, 300 times, okay? So these are sensitive zones which may fail And there won't be any detection of these things in the e-testing or any of the quality checks that supplier is doing because of the defect. If it is there, probably it's sub-micrometer, and it still allows the connectivity, it still allows a lot of things, but no detection. And it will manifest itself once we have a reliability test, or we send these boards to the PCB, to the customers. So it could come back as a field return. Okay. So these device PCB interactions are really important. Okay. So we'll not go into that. I'll come back to how we leverage on the usage of the analytics. Okay. So for today's call, we want to take up some example that we see a trace crack near the edge. So this is a plain view, and you can see this is the side view of the cross section. This is a plated through hole. So you can see there's a crack developed, and probably this is a very mild crack. It will open up after some temperature cycling. Okay. And here you could see certain examples and schematics, like what do you mean by PTH, plated through hole, buried via, micro vias, which are just below the VGA balls, the blind vias. Okay. And the sensitive locations are highlighted, which could be severely influenced by the manufacturing process. Okay, there could be trace residue of something, or there could be a stress which is developing, maybe like von Mises stress being developed during the bending, okay, forward backward bending when we're trying to do a temperature cycling. Okay, so it's not that the crack will never happen. Definitely a crack will happen, but depending on the mission profile of a particular device, maybe some devices, 600 cycles, temperature cycling is enough. For some of the automotive and military applications, we're targeting to get something like 1,000 cycles, or sometimes even 3,000 cycles, if this is really for military grade applications. Okay. For most of the automotive, probably something like 600, 1,000, 1,500 will do a decent job. Okay. But again, it really depends on the organization, the application of that particular device. Okay. So there's no right and wrong rule, and we have to optimize the cost, quality, and the time. Okay, right. Now, I think this was one of the questions for the poll, that what is the most dominant methods, or what are different methods which are used by the audience to really resolve this kind of problem. Suppose you find a trace crack, or you find a robustness. There's a thermal mechanical robustness which is being influenced, and we want to know from audience that what are you using in the different segments of the industry, for academia or for scientific research. Okay, so these are some of the things that we know, and I'll be more than happy to get your feedback and try to understand what more is being used and what is under development by the industry experts, the senior experts who are engaged in here. Okay, so Melissa, can we have the poll result available for this question one, just to get the audience some flavor that where do we stand, or you want to take it later on?
The poll question, Yichan, anyway, we can publish the poll question, the poll answer again.
Okay.
It is currently being shared, the results, poll results.
Okay.
To all the audience. Yeah, it's already live.
Okay, all right. So basically, first principle around 7%, Jump Pro 28%, Jupiter 5%, Analyst 2%, Sherlock 1%, 1%, and the others are 12%. We do not have the details.
Okay, great. So I'm very happy to see that a lot of people are using the Jump Pro, which is very encouraging. Okay, and those of you who do not have access to expensive commodities, I think you can see which version of the gem or which version notebook or other things are more convenient for you. Okay, all right, thank you. All right, so if you want to learn a bit more detailed insights, I think GEMP have a lot of webinars, and one of them I found interesting was the data mining and predictive modeling. So you can click on that and you can find a recorded video, and that really introduces a lot of things. But for today's call, I want to emphasize, okay, how we can avoid going to this traditional circle and do our simple mathematics using the different algorithms which are available and come to similar level of conclusion or similar level of quality, okay, without going into all kind of complicated detail. Like the traditional approach would be, we got a geometrical model, you do stress analysis, board level analysis, you can one stress analysis, and then you try to see, okay, how much stress being accumulated, release, and all this stuff. And eventually we come up with a model, and then finally we have a final solution. So instead of going that way, I personally consider there's a way to use GEMP to solve your problems. But here, we probably have to follow this kind of approach. First, we need to define what problem do we have. Are we trying to solve a trace which is cracking, or a via which is cracking, or we are seeing a delamination between the layers? Okay, what is our problem? And this could be PCB related, the substrate related problem. And then we try to generate different hypotheses. Okay, is it because of material, design, quality control? What are different hypotheses? And then we try to collect data, the data that we think is available within my company, within my organization. The data that we think your organization might have, but has not been digested. Okay, so that's why I on purpose quoted available data and the desired data. And I would strongly recommend not to explore the available data and to limit yourself that, okay, this is the data we have and this is what we have to model, and then this is the way we do. This is the way we have been doing past 10 years. I would say, don't do that. Leverage on your creativity, leverage on your subject matter expertise, generate all the valid hypotheses, 10, 20, 30, whatever you could, and get the desired and available data. Then you start to do the regression models, pairwise correlations, partial correlations. Probably I would strongly recommend to look for partial correlations because they show one-on-one correlation while keeping all the other influences low. Okay, then you can have other modelings like neural network, other things. Okay, and by the way, GEM 16 is coming up with a power of pretty much like 15 or 16 different kind of algorithms that you can run in parallel. Okay, so that's very, very powerful tool. Okay, so once we crunch this analysis, then we try to identify what is important. And take note, the order is not that critical at this moment. Okay, don't be controlled by this one. We really wish that people should consult with the subject matter experts, give a different ranking of the different variables. Okay, what we learned from the model, what we learned from the industry experience, what is our science or physics of failure telling us? What is the knowledge that we have brought in for last 10 years? Okay, then using all these variables, when we have it's more like running a prediction variable design engineering sort of thing. Okay, once we are done with that, then we try to do a Taguchi DOE when we have multiple variables and we know each type of PCB if we want to order that. So that would cost a lot. For example, let's say in Taiwan, if you want to order automotive grade PCB, there's something called minimum order volume. So you have to, even if you use one PCB, you still have to pay maybe 3,000, 5,000 US dollar or something like that to really get an automotive grade PCB. So that experiment is very expensive and there are tons of variables. So you have to be very selective. And I think in that way, if you use the Taguchi optimization, which is available within the GEMP, and also it's screening and a lot of other advanced analytics, which is available, I think that's really a smart move. Then our results can validate or reject the hypothesis. So if we wait, okay, the problem solved. We go to the next problem. Okay, the problems will never be resolved 100%. We will always have new problems, new challenges. Okay, so don't give up and let's continue, right? So now let's look at the data or some of the analysis that we did. So first of all, I'm going to show you some basic pairwise correlation. And we have masked the data. So don't look for the absolute number or absolute correlations. Just look for the thought process that we're sharing. Okay. So we have many variables. There were many of them. For sake of convenience of audience, we're showing the one which we're showing more recent correlations. Okay. So here, what we did a pairwise correlation and the partial correlation. I think this is one of the best things that GEMS offer, that you can look into which of these pairwise correlations are statistically significant, meaningful. Okay, you got some idea from here, and then you can other analysis. So you can probably E, D, T2, and P and L. This is important for me if I run a pairwise and partial correlation. All right, this could be my step one. Then the question is, where do I get all this data? All this data is available in our 10 years or suppliers' 10 years history. Every PCB supplier or a substrate supplier, they have last 5 years, 10 years record. They know the yield losses, they know the root causes, they know the design and engineering parameters, and a lot more things. So you can co-work with them, use their data, use your own product's data, and then try to come up with a comprehensive model to understand what is meaningful, what is worth spending effort. Okay. Now, data collection is always challenging, is always important, no matter we go through this predictive modeling using GEM, or we try to do a finite element analysis. Because there also you have to get all the variables of a material characterized. You have to key in the right segment at the right temperature, what's the right property, what's the right physical property. And if you miss a little bit, then there will be a garbage in, garbage out model. Model might look over promising, but the actual results, they don't fulfill. Okay. So if you want to collect all the basic data, probably it's going to take a couple of days. And once you have it forever. And if you want to run the finite element analysis, to my experience, it takes about maybe a week or even up to a month, no matter which platform you're using, because those are very tedious and although very accurate, okay, but very tedious and time consuming. So here, if you have this kind of data and this is available for you once and for all, and you can have your predictive engineering Excel sheet or predictive models that you could use for your new products as well. It's not just one-time activity, okay? Right? And you don't have to go through the iterative process. So once you have the model, you have the data available, probably next time when you want to run the model, it would just take you probably about 30 minutes to 1 hour for most of the simple scenario, maybe a couple of hours if you're doing with really heavy data, okay? But I believe MK do have certain solutions that can help you to reduce the time of computation. Okay, so we got something from Pairwise. That's the step one. Then we try to do the traditional least square fit model, and could see the E, D, P, L. They are coming up as a strong variables. Okay, and they're statistically significant. I think I probably have to drop it down somewhere. Okay. Then we also try to use the neural network. And this is, again, to give you an example that if you run the neural network, you can set up a neural network with different sigmoids or different step functions. You got a result, okay? Then you can go to the prediction and you can get the variable of importance. I think this is most people are familiar with, and you can maximize or minimize your desirability, and you get the variables which are important to you, okay? Then here comes the sweet part of that. You know, when we were doing with the GEM 15 and many other things, we were doing most of these models independently. And then there's some functions that somehow you can do a bit of a grouping of these results. Okay, that's called model comparison. But GEM 16 has really allowed that model comparison by just few mouse clicks. You don't have to do a very extensive thing. It's very user-friendly. And immediately you will see very easily, okay, these are different models, these are different variables, and okay, this is what I'm seeing. And let's go and discuss with our subject matter experts. Okay. Then this is again the question that we have. These are different approaches we can use. The variables patterns we got from model. You could have an AHP analysis, bug matrix, decision matrix. Okay, there could be different elements of cost, lead time. Okay. And once we are done, we are good to run a DOE. Okay, so we did our DOE with the Taguchi analysis. We did a 4-factor, 3-level DOE. Okay, And the results, although again, don't look at the number, these are kind of masked, but the important thing we want to share with you, that here by doing this analysis, we can understand the parameter E and C when they are on the high side, we're getting a high yield as well. And for D and P, we have to be playing a bit of optimum. So these are the process parameters, cannot be overdoing it or underdoing it because they both have consequences, okay? And this, of course, I can link these parameters to the physics of failure because we have done the modeling, what we call first principle calculations. So when I started this, I didn't have any software, neither JAMP, nor any ANSYS, nothing. So I started with my knowledge of physics. I really did all those first principle calculations. And eventually, when I got all the support and we got softwares, the models and everything all available. So we have a good understanding from different perspectives, okay? So we can relate these parameters to the physics of failure. So we understand, okay, it has to be optimized and this has to be high and does it make sense to our subject matter experts? So once this is clear, okay, then this is another illustration of the same thing. Okay, you can use a prediction profiler, you got a variable patterns, and you can see, you can make a Pareto sort of diagram for yourself and for the management. Because for management or some people who are not really technically into it, but they are really the one who will fund the project, who will be decision makers for us, at least for me, like an engineer like me, right? So we have to be able to communicate, okay, what is really important and what is really the pain or the benefits that we can have if we tune certain variables, okay, what do we get? So if you're able to connect to the senior management, to managers, that, okay, this is what we are looking for. We're looking for high time to fail. We will have a longer, robust time to failure. Our PCBs will be more robust, okay? Then we are in a good shape. And you can help to visualize, like in JAMP, if this kind of visualization, it also helps you to create different surface plots, the contour plots, to get a visualization. Okay, if I'm tuning a parameter C and E, what do I see? Do I see a valley kind of thing? Okay, for our case, I think it's more of a digital on-off kind of situation. Okay, as you could see that, okay, there's a red and gray here, and then most of the other situation is sort of green here. Okay, so it's more like a digital thing, but you could also have a contour plot, which may look like a valley, which may look like a really a target that we shoot. You know, if you remember going to a kids entertainment zones, there we have a lot of target we shoot, right? So that sort of profile could also show up. There could be valley, or there could be different segments that could show up. So it helps us to visualize what effectively we should do in terms of selecting the final parameter for the mass production, okay, and what we can achieve. So finally, we were having simple products, complex products. We were having a variation in the yield once we started to switch to complex products. And when we go through all the data analytics, when we go through the different discussions with the suppliers, so we didn't change too much on the BOM itself, okay, but we did change a lot of things in the design and the manufacturing, okay, and we were able to keep the cost low and get the good results. As you could see that before and after, we have a statistically significant difference, okay, the normalized yield is stable. And of course, you may say, yeah, okay, out of thousands of PCB that are ordered on the pilot run, maybe one of them might have a defect. Yes, I do acknowledge that. But for any pilot run, that the first time that design is there, so we are trying to be first time right. So if we are able to get 99% of those things correct without any defect, I think for the pilot design, it's more than good enough. There's no expectation for pilot run to be better than that. But mass production, of course, we should target the Six Sigma quality levels, okay? Right? So in conclusions, yes, we did a predictive modeling based on historical data. We ran a Taguchi analysis. We optimized the parameters, and we were able to resolve the problem of trace and wear crack. So you could see the time flows, prediction, variable, Taguchi, and we're able to pass. Okay. Now, it's almost coming to the end of this presentation. We will take Q&A. Okay. And there are a couple of things I want to share with you. For those within NXP, the NXP internal audience, if you're interested on the PCB competence, please contact with me. We have a full tutorial, which is about several weeks of hard work, but it covers everything from design to manufacturing to quality and everything that you might want to know about material to the finished goods. Okay, we have an internal competence certification course available. And if you want to learn about JEMP, then for the Asia Pacific zone, we have Jason Chen. He's actively leading the charge to really let people be aware how to effectively use JEMP. Okay. Now for NXP external audience, please feel free to raise some questions in this call. Okay. And you may contact me on LinkedIn. Okay. And if there are any opportunities for any kind of sort of research projects or any collaborative work that you might be interested to work with NXP on certain projects, please feel free to make a proposal or request in a genuine form, okay? And we might be able to help you out, okay? Now, if you have the JEMP related queries, of course, we have our MK, okay? And he's one of the experts in the Asia Pacific zone. So you should feel free to connect with him and get your questions on the JEMP result, okay? All right, so I wish to thank everyone in the JEMP team and also NXP friends and all the audience for being very supportive and joining the call today, all right? So this is not really the end of the word. We just wanted to give you different perspective. Like we started from very basic things, like what is the manufacturing looks like, what kind of defect we're trying to solve, and a comparative approach. And then we try to see, okay, this is the approach we'll see for problem solving, okay? And finally, we'll get the results. So it's more like putting a seed, giving certain information which we can share in a limited amount of time, okay? I think it's more of a seed for us to invite more communication to JEMP, more communication to NXP, and to help the automotive researchers, automotive industries. Okay, that's our intention. All right. So with these words, I thanks everyone. So Malika, I return back to you. Thank you.
Hey, thank you, Dr. Pradeep. Thank you so much for sharing with us. So we have a few questions, right? I'm not sure if you have access to the Q&A. Do you have access to the Q&A?
I can see that. I can see that.
Because I am not really sure which question would be relevant to your topic itself. There's a few questions there. Maybe you can skip the one with the jump. With regards to jump functionality, MK can help us with that. Maybe some few questions like there's one question from Philip Liduk. What about defects that are linked to the PCB layout itself? Do you also consider a virtual design of experiment approach deriving a ML model from the set of FEM simulations?
Correct. Yeah, I think that's the kind of thing we should all do. And let me just quickly browse through the questions, and then I can probably give some general answers.
Unfortunately, we are not able to share the recording of this session, guys. We are recording for the speaker, but we are not able to share you the video itself. So what we'll do is basically we will share materials or knowledge links that is related to the topic after this webinar. So sorry, guys.
Okay.
So any questions that interest you, Dr. Pradeep?
I think Philip, the Philip is asking a question which is very valuable to all the audience. Okay. The question he is asking that how we can make use of PCB layout, and then what kind of modeling could be done, and he's quoting about data scarcity. Yes, that's correct. So as I said before, we as a user or a new person, we may have a limited data, okay? But the PCB supplier, they have tons of data. So if I were you, if I have to answer this question, okay, what strategically I could do, I would rather say, okay, I would talk to my supplier and keeping all the confidential information as anonymous and going through genuine NDA process, non-disclosure agreement with them. Okay, then we try to collect all the historical data. What kind of designs, my design, other people design, they lend into the problem, and which designs which don't have problem. And then we try to leverage the machine learning algorithms to identify what are the intrinsic design weaknesses if you want to leverage on this kind of machine learning approach. Another way could be to see if your supplier allows the advanced analytics on the optical images and all those things. So if you go to GitHub, probably you may find there are certain algorithms that does show that how do we apply the machine learning and deep learning of different image processing data, different measurement data, and how to translate that into a particular defect or the risk of having a certain defect, right? So if you converge that way, I think there's some way to do that. But of course, as I say, this is easy to say, but it's probably is going to take you 6 months to 1 year to establish that. But once you have it, then you have it for a longer time, and you will be able to run it. Okay, I think that's basically. Then I think I would like to invite MK. MK, I think there are some questions which are more related to GEM.
Yeah, yep, to jump itself.
Yeah.
How about this one? There's one question that say that here we see that mean is considered. What if the parameter is cyclic? What measure can be used in this case?
The mean here is the mean of what we are talking about. I don't quite understand.
Well, I think he's probably referring.
I think it's referring to one of the slides. Yeah, because some of the questions came in during the presentation, right?
And is referring to the mean value what we saw in the DOE. So like, is this a time to failure? Okay. Then he's asking that here we consider mean. What if the parameter is cyclic? So that's a bit tricky for me to generalize in terms of our presentation. MK, do you have any thoughts on that?
For cyclic pattern and my past experience, I haven't come across such situation. So I'm afraid I don't have the answer to that. Yeah.
Correct. So in that case, I think it would be more appropriate to write an email to MK describing what type of cyclic parameter are we concerned, okay? And then we should be able to help out, because it seems a little bit not so clear what's the exact meaning of the cyclic parameter. Not sure if it has been explained in somewhere below.
Yep. Understand.
No.
Some of it are quite generic, right? So guys, don't worry if you can't, if we are not able to answer your question, right? So what we're going to do after this, we're going to export all the question. So hopefully we would have your email address here, so that those that we have the email address in the registration, we will send you an email and try to assist you with the question itself. Thank you, everyone. Thank you, Dr. Pradeep. Thanks all. Goodbye. Take care. Be safe.
Sure, everyone. Take care. Bye.
Bye-bye. Thanks, everyone.
Bye-bye, everyone.